So we have two methods we can program a robot, right? We can do what we call offline programming. And if you're enrolled in the simulation class, which is the T2, then we'll look at offline programming. But what we're doing this semester is we're looking at operation and actual programming of the real robot. So we're going to do what we call online programming. And anybody knows what that means? Now, what online means, which is what we're going on now. Well, say it. It's no big deal. I mean, having it on the test is one thing, and missing it in class is another, right? So this is.
I think offline program first.
Well, it's close. Online programming is when we go over to the robot and we write our programs on that using that teach pendant over there. That's online programming. Offline programming is when we write our program on a computer, put it on a USB stick or whatever's required by the robot, and transfer the program to the robot. Okay. So we write it using what we refer to as a simulation. So when you took Intro to Robotics, when you did those little programs, when you was building the robot, when you did those little programs in the controller, if you took, you hadn't took Intro yet, but when you take Intro Robotics, which is required for the certificate in robotics, you'll do online programming when you build the little Lego robot. Here, though, but that's very basic programming, but what I want you to realize is most applications, we can do almost everything that we do with online programming. We can also do that with offline. So we're going to use a simulation package called MotoSim. If you take the class. If you don't take the class, that's fine. It's not required. What I'm going to do is bring up one of the programs that we'll work on while we're in the class. Huh. Oh, wrong class. So that course is called Manufacturing and Computer Simulation. I teach all the robotics classes here. So I don't know what they're going to do when I retire. So this is, when this loads up, it's loading up off the network, so it'll take a couple of minutes. This is a simulation. So this is the simulated work cell for the Motoman robot. So if you look over there, there's the Motoman, and here's the simulation. And what we would do with this is we would literally write our program doing the simulation. This is the same model, so when you do the simulation package, you don't, the simulation program provides all the models that Motoman makes. And then what you do is you create a 3D image of the work cell. And then once you create a 3D image of the work cell, you place that robot in there. And then from then on, you come over here and you do your programming with the teach pendant. So I would come up here if I was going to do the program. Let's see. Then once we got the program written, then we would be able to execute it here. So what's nice about this is that once the program is written, and you'll do it exactly the same way on this teach pendant as you do on the teach pendant over there. And then what you do is once you got all the bugs out of the program, and any program that you usually write is not perfect the first time you try to run it. And the process of changing the program, we call it editing, and we're going to have some labs on how to edit a program. Also deleting and all this other kind of stuff. And plus you can check for collisions, so any workpiece that you place in here, so we got some where we have a box in here and stuff like that. And what you can do is you can detect collisions in your simulation. Well, if you collide in a simulation, that don't what? That don't hurt anybody. And like the analogy we use, it's like playing a video game. If you get killed in a video game, you're not really what? Dead. But, you know, so the military uses thousands of simulations while they're practicing, and they'll wear these vests and stuff like that, and they train you how to avoid getting killed. But in a simulation, you can practice it over and over and over again, but what they're trying to do is get you ready to go out in the real world, because out there, when you get killed, you're what? You're dead. So here, if we collide the robot, or if the robot doesn't do what we want it to do, we can make the correction in the simulation. And then what we do is we go over there, once we got all the bugs out of it, we go out there and upload it into the robot, and the robot runs that program. Just like we wrote it in the simulation. Now what's neat about that is, number one, the robot is not offline, and you're going to, offline means the robot's not doing the job I bought it to do. So when we do online programming, the robot is going to have to be offline. You companies don't like that, because why? Because when that robot's offline for me to write a new program, then that robot's not making me money, it's costing me money. So this is very, very popular, especially in applications where they've got hundreds of robots, where they go out and write the whole program on the simulation, and then but the robot is still making last year's cars, right? You understand? While I'm writing the program for what? For next year's cars. And so the bigger the place you go work in, odds are you're going to be doing offline programming. Now, offline programs are still not perfect, because your offline program, it is only as accurate as your 3D model. So if a welder goes out there and adds something out there, or they decide to do that, and the programmers don't add that to their model, then that means we're still going to run the program, but we still got to watch it, and we got to see what it did on the simulation. If it does what it does on the simulation, then we're okay, but we can also always touch the program up online, right? Does that make sense? And another thing that's neat is that if your program you're going to write is very similar to the program you already have, you can go over there and download the program from the robot and bring it into the simulation. And you can modify it in the simulation while the robot's still running the old program. That's what's so neat. And then when you finish, you can go over here and upload it, and it's ready to go. So the robot don't have to be offline while you're doing it. Well, we'll start off in this class. So this is the simulation class. If you're gonna take the simulation class, which is T2 for this term. But this term we're going to do online programming. So the smaller the company you work at, the more likelihood you're going to do online programming, because offline programming applications cost a lot of money. So one thing we got to do, and this didn't show up, can y'all read that? Okay, so what we have, number one is what we have, of course, and this should be in the jogging slide, is one thing we have the ability to select what we call modes of operation. And so this is either going to be selected on the controller, and I don't know if you can see it. So on the teach pendant, we select the mode of operation. On the KUKA and the Motorman, the switch is going to be a selector switch that's going to be on the teach pendant. For the ADB and the FANUC, the mode selector is going to be on the controller. So there's a selector switch. A selector switch is different than a push button, because a selector switch has multiple positions that you can put it Now the robots have different modes, but all of them have at least two. We have what we call the teach mode, which is also the manual mode. And this is where we're going to do what? Can y'all read this? This is where we're going to create programs. We can run programs. But when we run programs in the teach mode, that 3-position enabler, it says 2-position, 3-position enabler switch has to be held in the center position. And when you run the program, you can either run it cycle, which means it goes through the program completely, or you can single step the program. So single stepping is what we'd use to verify our points, right? Does that make sense? So if I wanted to go and verify every point, then I would use single step. If I wanted to see how the program was actually going to run, then we would use cycle. That makes sense? So we can create programs, we can run programs, we can edit programs, we can save, copy, rename, delete. I left delete out of there. So this is where we're going to actually create the program. You can't create a program in run mode. So the next mode we have is, we'll call it play automatic mode. This is a little different. This, you can select programs in here. You can abort programs, which means remove them from memory. You're not going to, if you abort a program, you're not going to delete the program out of the computer's memory. You're going to delete it out of the memory that is capable of, you're not going to delete it off that mass storage device out there. You're going to delete it out of the memory of the computer. Okay. Now, what you have to understand, if you've been reading that book, that programs are loaded into memory, and they're loaded off some mass storage device. So a USB stick would be considered to be a mass storage device. Okay. And then you run programs. You got to be real careful, like on a lot of tablets and a lot of cell phones. Once you run a program, it stays running in the background. And what do you have to do? You have to do something to go out and actually close it. So if you're playing a game and it starts skipping and stuff like that on your phone, what does that probably mean? Yeah, you got too many apps running in the background. So what you're doing then is you're removing it from the program memory and putting it into the mass storage memory inside your cell phone. That makes sense? Okay, so the play mode, we can load programs, we can abort programs or remove them from the memory, not from the mass storage. So you're not deleting the program, you're just removing it from memory. This is where the 3-position switch is not required anymore, right? You'll understand, because you're in automatic mode. That makes sense? Okay. And then, of course, safety interlocks are now valid. Up in the top one, I didn't put in there, but safety interlocks are the safety, we call them safeguard and e-stop, right? You understand? So e-stop is not considered to be what we call a safeguard. A safeguard, if you've looked at that safety lecture, which is due by when? Friday, midnight Friday. You're supposed to watch that safety lecture to get credit for assignment 3. So we have e-stop circuits, which means these are going to be your e-stop buttons or anything that when they set up the system, that they consider to be something that could cause injury. Then we have safeguard circuits, which only come into play when the robot's in automatic mode. So normally when we're in manual mode or teach mode, the safeguards are not in play. So that means you can open up the work cell, you can go in there, you can place objects in it, you can get in the work cell with the robot, right? You understand that while you're programming it. So a lot of times when we're writing programs, we have to be in with the robot, because we're trying to verify distances, we're trying to see if it grips everything correctly and all that kind of stuff. So this is in teach mode. When you jog the robot speed is limited to 250 millimeters per second. Okay, and why? Because that's been proven to be slow enough so you get your hand off that e-stop button if the robot is fixing to hit something, or you can, if it touches you and you're not paying attention. And people do that all the time. So safety interlocks are in place. That means if the program's running, then if you open up the door, what's the program do? The robot's going to do what? What do you think it would do? Stop. Are we okay? You can single step it in program mode, or you can run it in cycle. If you put it in cycle, then it's going to run the program from start to finish. Are we okay? So we'll be using these two modes. Some of the robots have more modes, but we're not going to get into those. So what is a program? So we're talking about computers. Anybody know what computers programs are? So what would be a program on the robot? Well, programs consist of what we call instructions. So a program is a group of instructions arranged in such a manner that will cause the computer, which is the controller, to perform a task. In robotics, so we have what we call programmers, if you heard that term. Those are people that write programs. So basically that's what you're going to be this semester. You're going to basically be a programmer. But when we create in computers, if you create programs, we call it programming, right? In robotics, we don't call it programming. When we create programs in a robot, we refer to that as teaching. So y'all going to teach programs. And that's what we're doing. So what we're doing basically for programming, and this is what we'll start out until we get to really high level stuff, is that you literally take the robot and you jog it to where you want it to go, and then you tell the controller to remember that point. And that would be teaching, right? What is syntax? Anybody know what syntax is? That's not S-I-N. So Alabama charges what they call syntaxes, which is that's what you pay on cigarettes and liquor and that kind of stuff. But in computers, syntax is not that. Anybody know what syntax is? In computers, this is very, very important. So when you take English composition and you turn your papers in, your instructor grades for content and they grade for syntax. Now, syntax is the correct way of writing something. So in English, what they're going to do is they're going to grade you on your commas, your periods, your question marks, your spellings. Well, that is syntax. Okay. So syntax is the correct way of writing in a language. That makes sense? So that your English teacher grades you on two things. They grade you on content to make sure you're writing according to the style that you were supposed to be writing in. And English composition is real fun if y'all haven't had that. Because they teach when I took it anyway, they teach different writing styles, and then you have to do a project on writing in that style. But they don't only grade you to see if it's in that style, they also grade you on your English, right? Your syntax. So syntax is the correct way of writing in a language. Now, with the written language, we can usually butcher the written language, and most of the time people can figure out what I mean. Right? You understand? But in computers, that's not true. In computers, when you write programs, in computers, which is a robot program, the syntax has to be perfect. Do y'all understand that? And we didn't have a time, last time we did intro, we didn't have time to do the Hero Labs, our mobile robot, and this is where people actually truly see syntax. You did, yeah, do the Hero. Yeah. So you're actually typing in or keying in all those instructions, and if you make an error, then when you try to convert it over, it'll come up and give you a syntax. If you've ever programmed in computer languages before, everybody that I know of has syntax errors when they try to convert the program. Online programming, teaching the program using the what? Teachpin. Are we okay? So what a program consists of, it's a group of instructions that tells the robot or the controller what we want that robot to do. We say tell the robot. The robot can't do anything. The robot is just a big chunk of metal that's got a bunch of servo motors in it, right? You understand? Who controls the show? The controller. Now you control the teach pin. I mean, you can use the teach pin, but remember, once you create a program and you turn that sucker loose, you have nothing to do with it anymore. That controller is going to run the program that you taught. So the controller is part of the show. We can use the controller to tell it what we want to do, you know, right? Like WordPerfect. Who's controlling WordPerfect? Well, I'm not controlling WordPerfect or PowerPoint. The computer's controlling WordPerfect and PowerPoint as an application that I'm running, right? Which lets us do a lot of neat things, but there's a lot of things that we just don't understand that we wouldn't be able to do. So, the parts of instruction, this is very important. The first thing, and it's going to be on the left, on just about all our robots, is something we call a line number. Now, what do you think the line number is? This is the order that the controller is going to do what? Run those instructions. That makes sense? The second part is going to be the actual command. And the first commands we're going to look at are going to be move commands. Now there's a lot of commands in the robot. But what we're going to do first of all is just learn how to make the dang robot move. Now we know about jogging, but jogging is not programming, right? You understand? If I had to have a person out there with that teach pin moving that robot around and telling it to open and close or move around, then I might as well have a person doing the job. In fact, the robot will probably be slower, right? You'll understand that. So what we're going to do is the commands we're going to start out is what we refer to as move instructions. Of course, these instructions are going to tell the robot how we want to move. We want it to move. Okay. And we'll look at these, but there's basically three on all these robots. We have what we call a joint move, we have what we call a linear move, and we have what we call a circular move. Now some robots support more, none of them support less. So we'll learn about these moves, and we'll find out anything we want this robot to do, we can do with these three moves, which is pretty neat. Because if we had to do tons of moves, it would be hard to do, but now that I've got these three, it makes programming the robot or teaching the robot a lot easier. Then after the command, so we start off with a what? A line number. Might be 1. Then out here, I might have a move instruction. And then after that, we need to put some information about that move instruction. What's some of the things you might think we might want to tell? Well, we're not going to stop it because a move instruction is going to make it move. Once it executes the move instruction, then it'll drop down to the next instruction. Now, we might have a stop instruction. So we might say move, and then the next instruction might be stop, right, or end. Most of these robots use end to tell the program, but you're not telling the robot to stop, you're telling the program to stop. So what are some of the things you do with your car when you tell your car to move? If you want to tell your car to move, what's some of the things you would do? Well, first of all, before you turn the steering wheel, you tell it which direction, right? So, of course, you sometimes you select, so which direction you want it to move, or where do you want it to move to? So here we're going to say, okay, where do we want it to move to? So that's got to be part of this instruction, right? What's another thing? Once you tell it where you move, then you have to tell it that would be part of the direction, like when we say where we're going to move to. Then what do? So you get in your car, you put it in drive, right? Right? You turn the wheel, so that would be telling it where you want to move to. And what's the next? Then you do what? Press gas. And then the gas determines the what? Or the speed. Good. Okay. So this has got to be part of the move instruction. We got to say, okay, where do you want the robot to move to? And how fast do you want it moved there? Okay, so that would be information that's required by the move instruction. Huh? Well, not axis, because now what we're doing is moving the robot. Now, when we jog the robot, we have what we call a joint jog. Now, don't get the joint jog and the joint move confused with each other. They're not the same. Because jog, I'm coming up here and I'm pressing buttons and I'm calling. When I tell the robot to do a joint move, the robot's going to move. The controller determines what axis it needs to move to get that thing to the point, to the position that we told it to get to. So joint move would be like I have different controls on my car that controls the left wheel and controls the right wheel, right? It's kind of like, I don't know if y'all seen some of these big old rock climbing cars where them suckers can control every wheel individually, try to make them things crawl up over them rocks. Well, that would be like a joint move. So I'm responsible for this wheel or this brake or that brake, right? Some of those monster trucks that jump over tires, they control the wheels individually. So they can swing the back wheels this way or they can swing them that way. So they actually have two-wheel steering, right, where they control the rear and back wheels. Well, that would be like a joint job. A joint move would be like me getting in this Tesla or whatever that's coming around and tell it I want to go to Walmart, and the car does what? Drives me there. Now, what the car is probably going to do is it's going to monitor the speed limit and all kind of things to get you there, right? You understand? So in our move instructions, we don't tell it what axis. All we're saying is I want you to go to that point. And then the controller figures out what axis to move to get you there. So as soon as you switch this sucker, as soon as you run a program, you're not controlling the axis anymore. Who's controlling the axis? Well, that controller is controlling the axis. All we can say is, okay, I want you to go to this point. I want you to go at this speed. And then there's some other stuff we'll use. Well, the point itself, the position, would be what we call a constant. Now, in programming, a constant is something that you cannot change without changing the program. So it means I come up here and I tell it to go to this point, and I say, well, that's the wrong point. Well, what I would have to do is I'd have to move it to the new point and tell it that was the new point. Well, what I did is I just changed the program. A variable is something that we can change without changing the program. So we can do this from the teach pendant. So one thing we can do from the teach pendant is that we can change the speed. So if I tell my robot to move at 100% in my program, or what I can do on my teach pendant is I can say 50%. Well, if I set it at 50% and the program says 100%, then now 50% would be my override, right? You understand? So the speed on the robot is going to be a variable, but the point is going to be a what? The type of move is going to be a constant. Because if I go in there, if I want to change from a joint move to a linear move, you have to change the program. That makes sense? So it would be like you engage the cruise control on your car. And of course, when you engage the cruise control on your car, you can't slow down, but you can still do what? You can still speed up. So if it's not going right or you want to get around a truck or something real fast, I learned real fast on riding on motorcycles. You never ride beside anybody. If you ever ride a bike, don't ride beside you. So you stay behind them when you get ready to go. If they're going pretty slow and you want to go around them, you don't fool around. You don't ride side by side because they can't see you a lot of times. Sometimes these information is not required. Like we said, is like if I wanted to tell the robot to stop, or if I wanted to tell my program to end, there's no information required for that. I mean, I just tell my program to end. I don't have to say end on Tuesday or Thursday. I just say end, right? So some instructions do not require. So the things that are required is the number and the instruction. Then we might have to provide additional information depending on what that instruction needs. So a move instruction is going to have at least two things. It's going to have to say what? Where I want to move to, and how fast do you want to make that move. So these are the basic parts of instruction. Are you okay? So first of all, creating a program. Number one, we have to give it a name. So when you download an application for your phone, that application has a name. Well, how did it get the name? Well, the creator of the application did what? Gave it that name. So you're going to be creators of these programs. So when you create a program on this Teach Pendant, what you're going to have to do is what? Give it a name. And of course, this is the way we'll load the program. We load the program by name, right? We delete the program by name. We copy the program by name. We edit the program. We have to load it in the memory to edit it. So these names are pretty important. We had a guy here that when he not when he created programs. So when you save files, like if you got a word processor. By the way, I'll try to find that email. If you're enrolled in the college, you can get Microsoft Office for free. All you need to do is have a valid email address. They call it Office 365, and it's really neat, which is the whole Office suite. You can get it for free. Well, I'll try to find that and post it on my website. It's really neat. I use it on my computer at home. Yeah. Especially when if you're in the degree program, you got to take that CIS 146. Guess what they teach? They teach Microsoft Office. It would be real neat if you had that on your computer at home. That would make it a lot easier for you to practice and actually do some of your projects instead of trying to do them in class. Well, when he saved the documents on the computer. That you have to give them names too. So every time you save a document, you have to give it a name, which would be basically the same thing. And he gave them names like ping pong and ding dong and stuff like that. And we had no idea what they were. So when he retired, guess what we had to do? We had to open up every one of those documents to see what they were. But he knew what they meant. The username. So we're going to make sense. All ours are going to start off with like Lab 12. And you're going to use like your initials or something like that. So that way you'll know right off the bat which labs are doing. The name has a link. Originally, when they came out with our DIS operating system, which we used to call a DOS, you were limited to 8 characters for your names. Unfortunately, some of the robots took that same feature. Some of the robots in here, you're limited to 8 character names. And so that's what we're going to do. So to make it easy for me to grade, we're going to set the length of the name for the smallest that these robots support. Does that make sense? And then everybody's name will look the same. Some of them are like Windows now. Good gracious! In the old days, we were limited to 8 characters, which seemed like an infinite number of combinations, because you had 8 characters. So you had 8 characters, and you could use numbers and letters. So that would be 8 to the 36th combinations. And punch that baby into your calculator. But the problem is that 8 characters, it seems like you got all these name combinations out there. But the problem is you're trying to give it a name within 8 characters, which means something so you know what that program does. So it was real hard just trying to do that. When they came out with Windows XP, they changed that to, I think, 128 characters. So you can basically say, well, this is a program I wrote on April the 4th that did this. And so these are really, really neat now because you can really give it a long name. But we're going to limit ours to 8. A lot of the punctuation carriers are not allowed, and this is still true even today. So there's some punctuations you cannot use when you create file names because they mean something else. So for a long time, we used punctuations to tell the computer to do something, like slashes. So you can't use slashes as a part of your name because a slash usually tells it to take a path, right? It tells your computer that you want to go this way. Some robots require a folder to be specified. So a lot of these guys like the KUKA and the AVB work very similar to Windows. So Windows, we create what we call folders, right? You understand, and then we put information in folders. So if you work on the AVB, then what you'll be doing is your programs are going to a folder that's created for this class, and I'll make sure that that folder is created. We can do that on the KUKA too, but normally we just put it in what we call the root folder. And of course, consult the appropriate manual to determine the procedure. So that's one of the things we're going to do in this class. We're going to say, okay, look up the procedure in your manual that tells you how to create and name a program, right? Of course, that's what we're trying. Teaching, move the robot to the position required by the program. And so all our robots are what we call point-to-point robots. So what a point-to-point robot does is we teach it a point, and we tell the robot, the controller, how we want to move to that. And that would be that move instruction, right? You understand? So what we'll do is we'll move the robot to a position required by the program. Okay, so what we're going to do is we're going to jog the robot, and we're going to jog it using either joint, or we're going to jog it using either world or tool, which we very seldom use in this class right now. So these are the two predominant right here. When do you use joint? Well, we're going to use joint if we want to move one axis. We're going to be world. What advantage does jogging the robot in world mean? Because all we're doing now is specifying a direction, right? So we're not concerned with what joint to move. All we're trying to say is I want to move it up, I want to move it down, I want to move it toward me, I want to move it in and out, which makes it real, real easy. Note that the programming point can be edited, deleted, moved, and copied later on. So later on, we'll start off by doing programs. And if you screw up when we're first learning just a program, then I'll come in and I'll take care of it for you. But once we learn how to create a program, then we're going to learn how to modify it. We're going to learn how to edit it, which would mean reteaching points, changing speeds, changing point numbers, all kind of neat stuff that we would do if I was an actual programmer. We're going to learn how to delete points. We're going to learn how to copy points. We're going to learn how to delete programs and all that other kind of stuff before we move any further. Teach pendant, teach the point using the required move. So in here, we're only going to use 3 moves, which are supported by all our robots. We call those joints linear and circular. We're going to modify the move instruct. By the way, this guy here, it's not as hard as you think it's going to be because they understand a lot of people that program robots don't have a lot of programming experience. So what happens is that when you tell it you want to move, you're going to get an option, a menu of the type move you want to do. And when you select the type move, it's going to insert that instruction into that program for you with the right syntax. Now the problem is that it's going to use a set of what we call defaults because it's got to know certain conditions, right? Default. What is a default? Anybody, a default in computer programming is what the computer uses if you don't tell it any different. So when I come up here and I load in this application called, well, we can do it here. I mean, so I can come up here and let's just abort this program. So we're going to discard all that. And I didn't want to save it. Okay. So when I come up here and load this program in, this is an application. That I just had up. I shouldn't have carried it down, but that's okay. PowerPoints. And we're looking at basic programming, right? And all I'm going to do here now is just insert a slide. So right now, if I start typing, we got a lot of stuff that we can specify about how I type. One of the things is what we call a font. So this is the default font. So what does that mean? That's what the application is going to use unless I tell it something different. So if I come up here and type in, it uses that font. The other thing we have is what we call the pitch. The pitch is the size of the character. So when I come in and load in this application, it's got to know information. It's got to know what font I'm going to use, and it's got to know what pitch I'm going to use. So what does it do? It loads in a set of defaults. If I don't like those defaults, then what can I do? I can change them. So when we create a move instruction, it's going to pop a set of defaults in there. So it's going to put in one thing it's going to do. It's going to set a default speed because that's required by the instruction. So if the computer is going to put the instruction in there for me, it's going to put some defaults in there. And it's up to me if I want to change the speed. Then I have to do what? I have to modify the instruction. Does that make sense? Everybody okay there? Any questions on that? So I can come up here. I drop down here. It uses a different pitch, but I can come up here anytime and I can change the pitch. So if I wanted to make it smaller, now I'm using a smaller pitch. But if I was to open up another document, it would come in and use what? The defaults for that application. So we have to do the same thing when we do our instructions. We have to do what? We're probably going to have to, so this is what we do when we, oops, sorry. So we're going to teach a point using the required move. So what I'll do is when I say that I want to teach a point, odds are we're going to get a menu where we can specify either what? A joint, a linear, or search remove. Once I select that, it's going to put that move into the program for me. Then I'm probably going to have to do what? I'm going to have to change some of the defaults to what I want it to be for my program. And one of the things might be speed. This is definitely going to be true. And then later on, we're going to talk about accuracy. And then many taught programs require other instructions besides move instructions. So, well, what we're going to start off with is we're going to learn how to create a program by giving it a what? Create a program, naming the program, and then teaching our first program. So, got any questions? And of course, we'll look at it later on. So let's say I wanted to open the gripper. So if I wanted to open the gripper, that's not a move instruction, right? So what we'll have to do is we'll start off with nothing but move instructions. And then as we move on, we'll teach you how to access the outputs and inputs on the robot so you can open grippers and close grippers and all this other kind of stuff. Teach you how to make the program loop. So most programs are what we call a straight line program. And what that means is we'll come through and the controller will run it one time and then it'll do what? It'll stop. Well, what if I wanted it to do the same thing over and over and over again? Well, we've got other instructions to tell it to do that. So later on, we'll learn how to make the program loop. We'll learn how to do that. But what we're going to start off with is just learning how to teach points. And then, of course, how to modify the points. Okay, guys, y'all take a break. I think I left the thing recording. Joint move moves the tool center point from the previously taught from the previous taught point. That's I'll have to upload this. There's several errors in this that we'll have to recreate. I'll come up and re-upload them to the website. Moves the tool center point from the previously taught point by running all joints at the same speed. Tool center point will follow what we call a non-controlled path, and then we'll have to specify accuracy. But accuracy is something we're going to talk about later. You'll see that. So joint move is what we call an uncontrolled path move. You don't have to worry about singularity because the robot is not trying to do any math. It turns all the motors on at your indicated speed. Now what happens is some of your joints get to positions before others. So what that means is the path of the robot is not going to be in a straight line. But your joint move, this is the ability to move the robot the fastest that it'll move. And the analogy we would use, so let's try to do it. Everybody put up here, let's come up with 2 points. 2 points. Everybody put your hands up. Okay. Now try to move between that 2 points and try to maintain a straight line. How fast can you go? Not very fast because your brain is doing a lot of work, right? Now don't care how you get to that other point and move it as fast as you can. What happens? You usually move in an arc. You don't move in a straight line. You know, a lot of people say which is the fastest. And a linear move, we say a linear move is a straight line and a joint move is not. And most people say, well, it's a linear move because it's a straight line and it's the shortest distance between 2 points. And I say, okay, so that means I can go from here to Birmingham and I can go the highway up here and they turn all the red lights red and I do 100 miles an hour up here. Or I get on the interstate over here and I'm limited to 30 miles an hour. Which is so one of them is pretty close to a straight line. The other one, we're going through all these cities and it's got curves and everything. It's not a straight line. So you can't say the fastest speed is the straight line. So we went to, of course, Highway 65 is not a straight line. But when I would ride my motorcycle down to Gulf Shores, my wife would go down 65 to Gulf Shores. And I'd take I-5 and hit all them back roads. There was a curvy road down there it was one of those foot peg dragging curvy roads. I don't know if y'all ever rode a motorcycle and leaned over so far that your foot pegs drag on the curves. Yeah. I'd beat her down there every time. And why? Well, my wife does the speed limit for number 1. So, but I did it what? I did it faster. So the joint move is the fastest we move the robot. The only problem is that when we teach the point, we don't know how it's going to move today. Now, once we run the program, we can see the path. It will always follow that path, but we don't know it, right? You understand? So we consider it an uncontrolled math move. It will not be a straight line. It's going to be some type of curve. It's going to be some type of S, but it's not going to be a straight line, but it's going to be the fastest I move. So normally what we use this joint move for is we're going to start the robot in what we call a home position or a start position, and then we're going to be working down here. Well, usually we use joint moves to get it down to where we want to go and get it down there as fast as we want to do. And then how fast we move it on our workpiece depends on the job, right? Does that make sense? So all we do on a joint move is we specify a percent speed. You don't specify the speed. You specify a percent speed. So if you have your teach pin that's set to 100% and you tell it to do 100% move, 100% speed move on a joint, you'll see the robot move as fast as it possibly can. So some of these robot moves on the big FANUC over there, these are joint moves. But when we get down and start following the path, we're going to move over to a control path move. So the next move is what we call a linear move. The tool center point will move from the previously taught point in a what? Straight line. Now this is a control path move. We're going to have to slow this sucker down because now the controller is going to have to do a lot of math, right? You understand? Here you specify the speed. So you say 100 millimeters per second, you say 250 millimeters per second, you say 1,000 millimeters per second, and it will move the tool center point at that speed. Now what speed the actual axis move at will depend on the controller, because, you know, a while ago, I'm not moving this guy hardly any, right? You understand? So it wouldn't move this one very fast. This guy here is gonna move the fastest because it's further back, right? You understand that? So what here is we don't specify a percent speed, we specify the speed of the tool center point. The controller calculates what speed it needs to move each axis to cause that tool center point to move in a straight line. Then we have the last move that we'll teach this semester is what we call a circular move. It's actually misnamed. This won't draw a circle, it draws an arc. And an arc is basically a curve that passes through 3 points, right? You understand? So a tool center point moves through an arc that includes 3 taught points. So we have a start point, we have an end point, and then we have a center point. And then it moves through those 3 points, and what's it going to do? It's going to do an arc. So if I wanted to teach it to draw a circle, I would have to use 2 circular moves. Because it don't do a circle, it does a what? It does an arc. We have to specify the speed we want it to move around that arc, and we'll talk about accuracy later on. So these are the 3 moves. How many of these robots support those moves? Everyone. All I got to do is figure out how to teach that move on that robot that you're assigned to. I have to figure out what speed I want it to run at. Of course, in the labs, it's going to specify the speed. When we do joint moves, that's going to be what? That's going to be 100%. Okay, guys, let's go over here and look at some of the robots. And we got more on this lecture, but y'all need to work on y'all's jogging labs.